4.5 Calculus 1 video lecture on applied optimization. So in the previous sections, we talked about how to find the extreme values for a function using the first and second derivative. So today what we're going to do is talk about how to find, how to optimize an actual real-world situation using calculus and our graphing calculators to help us out. So, steps suggested by the text for solving optimization problems are: first, read the problem. Make sure you read the problem until you understand it, what is given, what is unknown, quantity to be optimized. Draw a picture that can help you visualize what's happening. Introduce a variable, so list every relation in the picture in the problem as an equation or algebraic expression and identify the unknown variable. And then write an equation for the unknown variable. If you can't express the unknown as a function of a single variable or in two equations and two unknowns, this may require considerable manipulation. Test the critical points and endpoints in the domain of the unknown. Use what you know about the shape of the function's graph. Use the first and second derivatives to identify and classify the function's critical points. So, here's an example of doing that. So we're designing a box with a lid. So a piece of cardboard measures 10 inches by 15 inches. Two equal squares are removed from the corner of a 10-inch side as shown in the figure. Two equal rectangles are removed from the other corners so that the tabs can be folded to form a rectangular box with a lid. Okay. So what we've got here is we've got the base of what will end up being our box, but it's made out of one big rectangle that's 10 inches by 15 inches, and we're cutting out squares and rectangles to turn this into a box. So in the end, what will happen here is we'll have be able to fold this into a three-dimensional box that looks something like this. Okay. So, write a formula for the volume of the box. So, volume is equal to base times height. So, the area of the base times the height. In this case, that's length times width times height. So, now what we need to be able to do is we need to be able to describe each one of those things, length, width, and height, using the variable x. Okay, so a fairly easy one here is that if you look, x are these lengths here. All of these are x's. And these are the pieces of the box that make the height. So h is equal to x. So then the width of the box is this piece right here. So the width is going to be whatever this 10 inches is that the whole piece of rectangle minus the two pieces we take out. So the width is going to equal 10 minus 2x, right? Because we've got 10 inches total and we're taking away 2 x's. And then the length is this side here. So that's going to be 15 minus some things. Okay, so that's going to be a little harder to work out, but the thing you want to notice is this is also the length. So if you think about it more as what does 15 equal? Well, 15 equals an x here, a length here, an x here, and a length here. So that would be 2l plus 2x. And now we can solve that piece for L. So that ends up, subtract 2x from both sides, so 2L equals 15 minus 2x, and then divide by 2. So L equals 15 over 2 minus x. Okay, and so now that we've written h, w, and L all using x, we can substitute those into our volume function. So we get v of x equals length 15 halves minus x times width 10 minus 2x times height x. So now we can find the domain of this function that we're dealing with here. So in this case, for the example we're looking at here, the smallest x could be is 0. So that was part A. So now for part B. So the smallest x could be is 0, right? And in fact, x can't actually be 0, because if we let x be 0, then this makes no sense, right? If you don't cut anything out, you can't make a box out of it. It's still just going to be a sheet of paper. And the largest x would be 5, right? Because if x was 5 and x was 5, then this would be 0. The width would be 0, so that wouldn't work out. So the biggest x can be is 5. So there's our domain. So our domain is 0 to 5. Okay, so now it says use a graphical method to find the maximum value and the value of x that gives it. So what we can do is we can go into our class calc app, and we can graph this. So let's graph. So y equals 15 divided by 2 minus x times 10 minus 2x times x. And we only want to look at this in the domain 0 to 5. Okay, and we can see that that gives us this graph right here. And if we zoom out, we can see that it has a maximum value, and that maximum value is happening at the point 1.96188, so 1.96, comma 66.02. So 1.96 and 66.02. So the maximum value, the maximum volume equals 66.02 cubic inches when x is 1.96 inches. Okay, and now we can verify that by using analytically. So when they say analytically, they mean use calculus to verify that. So for part D, we just want to take, and the easiest way it's going to do this is to multiply this out, right? So for part D, multiply out our volume function. So v of x is going to be 15 halves times 10 is 15 times 5. So that's 75. And then we also have an x of 75x. Minus 25x squared plus 2x cubed. Okay, so I believe if you multiply that all out, that's what you should get. And so now what we want to do is to figure out the maximum value of this function. We want to take the derivative, so v prime of x, so that would be 75 minus 50x plus 6x squared. And so now we can use, we want to set that equal to 0. And we can use the quadratic formula to solve that. So that's going to be x equals 50 plus or minus the square root of negative 50 squared minus 4 times 6 times 75 all over 2 times 6. And then because we're dealing in applications here, if you want, you could try to simplify that for an exact answer, but we're really just trying to verify the decimal answer that we got using the graph. So you could just plug that into your calculator. So if I do that, this will be 50 plus the square root of negative 50 squared minus 4 times 75, 4 times 6 times 75 all over 2 times 6. And when we do that, we get 6.37, which is too big, right? Because that's not in our domain. So now what we want to do is if you double click on that, it'll give you the whole thing again. And now we want to just change this to a minus. And if I hit enter, I get the answer I'm looking for, 1.96. So when we solve this, we get x equals 1.96. And then if you want to find v of 1.96, so we plug that into our v, into our original equation. So 75 times 1.96 minus 25 times 1.96 squared plus 2 times 1.96 cubed. And we get 66.02, exactly what we got over here. So that basically shows you the two different ways you can go about solving this. You can use your ClassCalc app once you've got the function to graph it and look for a maximum, or you can use the analytical approach using calculus. And it's not a bad idea to do it both ways so that you can compare your answers for checking. Okay, so that's the idea of what we're doing in this section. So let's go ahead and flip over to the next page and try a couple more of these together. Okay, so 26 says, compare the answers for the following two construction problems. A rectangular sheet of perimeter 36 centimeters and dimensions x by y is to be rolled into a cylinder as shown in part A of the figure. What values of x and y give the largest volume? And then for the same sheet is to be revolved about one of the sides of length y to sweep out the cylinder as shown in part B in the figure. What values of x and y give the largest volume? Okay, so those are two different problems we're going to look at. But the formula we're going to be using here, or at least one of them, is the volume of a cylinder. So the volume of the cylinder is exactly the same as the box we did on the last page. It's the volume equals the area of the base times the height. But in this case, the area of the base is a circle, so that's pi r squared h. Okay. So what we need to do is we need to fill in these formulas so that we're only using one variable. So for part A, in this case, in our cylinder, y is equal to h, and x is the circumference of the circle. So we need to relate that to r. So that would be c equals 2 pi r is the formula for circumference. So x equals 2 pi r. So x over 2 pi equals r. So x. So we've got those two. Now we've replaced the variables in this function with x and y. So this would be v equals pi times x over 2 pi squared times y. But we've still got too many variables in there. So we need a way to rewrite x or y using the other one. And that's where the perimeter comes in. So perimeter equals of a rectangle 2x plus 2y. And so if we plug in 36, we can solve for y so that we can substitute it in the function. So if I subtract 2, so 36 minus 2x equals 2y, and then divide by 2. So 18 minus x equals y. And so now we can substitute that in for y. So we get volume equals pi. I'm going to multiply this out. So x squared over 4 pi times 18 minus x. Sorry, there should be a pi squared there. And then we can simplify that a little bit and multiply it out. So if you simplify, the 1 pi cancels here, and then we can multiply. So volume equals 18x squared over 4 pi minus x cubed over 4 pi. Okay, and now what we want to do is, if we simplify this, take the derivative. So v prime would be 36x over 4 pi minus 3x squared over 4 pi. And then we can simplify this a little bit and set it equal to 0. 36 divided by 4 is 9. So this would be 0 equals 9x over pi minus 3x squared over 4 pi. And then we can factor a little bit and solve. So we can factor out 3x. So this is 0 equals 3x times 3x over, sorry, not 3x. 3 over pi minus x over 4 pi. Set those both equal to 0, and we get 3x equals 0, and 3 pi minus x over 4 pi equals 0. Solve this one on the left by dividing by 3, and you get x equals 0. Solve this one, you subtract 3 pi from both sides. So it's x over 4 pi equals negative 3 over pi. And multiply both sides by negative 4 pi. So x equals pi's cancel. Negative 3 times negative 4 is 12. So in this case, x equals 12, and then we can plug it into this perimeter formula, 18 minus 12, and y equals 6. So 12 inches by, not inches, centimeters is the units in this problem. So x is 12 centimeters, and y is 6 centimeters. Okay, and so that's all there is to that part A. And once again, once I got the function over here, if I wanted to, I could simply graph that and look for the area. Also notice we did get a second answer here, which is x equals 0, but does x equals 0 make any sense? No, because that wouldn't be a rectangle, so we're not going to use that answer. It's a fine answer to the equation, but it's not an applicable answer to this application. Okay, so then we can try part B. So for part B, it's the same idea, but now we're talking about this circle down here. So when we plug into our formula here, the volume, we're still going to use the same formula for volume, but in this case, our x is actually our radius, and our y is our height. So this is going to be a little easier to plug into the formula. So the volume is going to be pi x squared, and then for height, I'm going to use this 18 minus x. That equals y. And then we do the same stuff we did over here. So I can multiply that out. So v equals 18 pi x squared minus pi x cubed. Set it equal to 0. And, first take the derivative. So the derivative v prime is 36 pi x minus 3 pi x squared. Set it equal to 0. And we can solve. So factor out an x, 3x. So 3x times 12 pi. Actually, let's do this a little easier even. I can take out a 3 pi x. So 3 pi x, which, looking back on the other one, I could have taken out the pi too, but we didn't, but that's okay. You get the same answer either way. And that leaves me with 12 minus x. So we get 3 pi x equals 0. So x equals 0. And over here we get 12 minus x equals 0. So x equals 12. So x would be 12, which means y, once again, has to be 6 centimeters. Okay. And so that's the idea. So the basic difficulty of these problems is figuring out a way to write an equation for the function, for the formula that you're looking for that involves only two variables, the output and one input variable, so that you can graph it or use calculus to find its maximum value. So that's where one like this next one gets tricky. Okay, so let's go and look at this next one. So this one says a cone is formed from a circular piece of material of radius 1 meter by removing a section of angle theta and then joining the two straight edges. Determine the largest possible volume for the cone. So this is basically like we're making a snow cone, right? Or one of those drinking cups. That's how they basically make this, is they cut a triangle out of a circle and then they merge the two pieces together. So first of all, off the top here for this problem, the volume of a cone, let me use a different color from either of the ones above just in case these get too close together. The volume of a cone is 1/3 pi r squared h. So basically the volume of a cone is 1/3 the volume of the cylinder that it gets cut out of, is kind of the idea where that formula comes from. Okay, so now what we need is we need a way to plug in, we're worried about this theta, right? We want to know what is the best angle theta that gives us the largest possible volume. So in order to do that, we want to rewrite r and h using theta. Well, the first thing we should talk about is that this piece of the circle all the way around is the same as the circumference of this circle, right? Those are the same thing. The circumference of the base of our cone is the same as the part of the circle that's left over when you take this piece out. Well, we can figure out that value, so that c is going to be equal to the whole cone. So that c will be equal to the whole cone, which is 2 pi r, minus the piece we take out. And the piece we take out is theta r, right? So the length of an arc is its angle in radians times the radius. Okay, so that's the formula for that. So, but now we can plug in 1, and we get that c equals 2 pi minus theta. Okay, so that means so that's the beginning of this problem. So that's the first thing we need to notice. The second thing we need to notice is that inside of this cone, if I were to do a cross section of it, it would look like this. Okay, and then this would be the radius of the circle, and this has a length of 1. So another really useful piece of information here is that we can use the Pythagorean theorem to write an equation that involves r squared and h. So that would be 1 squared equals r squared plus h squared. And then also, if we look at this circle here, we know the circumference of this circle, which is equal to this c, can also be written as c equals 2 pi r, where r is this radius, the radius of our new cone, which would not be 1, right? Because 1 is the height, is this long side, so r's got to be less than that. So now we can go over to our equation over here that we wrote that tells us the length of this arc here, c, and that's the same as this c. These c's are the same, so I can plug 2 pi r in here. And if we solve for r, then we get r equals 2 pi minus theta over 2 pi. And if we solve this formula for h, then we'll get h squared equals 1 minus r squared. So h equals the square root of 1 minus r squared. And we can plug r in there as well. So we get h equals the square root of 1 minus 2 pi minus theta over 2 pi. And now we've got a formula for h and for r that both use theta instead, so I can plug that into the volume function here. So the volume is going to equal 1/3 pi times 2 pi minus theta over 2 pi squared times the square root of 1 minus 2 pi minus theta over 2 pi. And so now this is a formula for theta that, for volume, that only involves theta. Okay. Now, what you could do is you could work through this using calculus and do the analytical approach and do this derivative if you wanted to. I would not necessarily suggest that. So what I would do at this point is I would graph this, replacing x for theta. So this is going to be, if we go to our graphing function on our calculator, it's going to be y equals, so y replaces volume, 1 divided by 3 pi times 2 pi minus x over 2 pi squared times the square root of 1 minus 2 pi minus x over 2 pi. Okay? And you just want to make sure you're in radians. So here's what the graph of this looks like. Now, one of the things you want to think about is what is the largest theta could be. So if we go back to the problem before we look at the graph, what is the largest you can make theta to be? Well, the largest it could possibly be is 2 pi, right? Because that's a full circle. And the smallest theta could be is 0. So 0 has to be less than theta has to be 0 has to be less than theta, which has to be less than 2 pi. And 2 pi is approximately 6.28 if you just multiply 3.14 by 2. So if you look at our graph here, we can go ahead and make the graph do that as well. So let's set the domain to be from 0 to 2 pi. Okay, and notice, just a couple reminders, the way I did that is I click and hold down on the colored circle there, and that'll bring up the option to set the domain. And so now I can see my graph, and I know this highest point is my maximum. Although, ooh, I forgot something in my equation, I think, because I'm like, that's not the right answer. I forgot the squared, right, on this, when I substitute in, so right here, I forgot the squared on my r squared. So let's add that into our equation here, and hopefully that will fix our problem. Okay, so now that we've got the function and we have it graphed here as shown, we can see that the ordered pair 1.15299, 0.403067 is the theta and volume. So for this cone, so we get the maximum value in our domain at 1.15, let's call it 1.153, and 0.403. So to answer the problem, what is the largest possible volume? The largest volume, the max volume, is 0.403 cubic meters. Okay, so now that we've had a chance to do a few of these together that are along this idea of volumes and dimensions, why don't you all take a moment and look at the two problems on the next page, page 31. Pause the video, try these two on your own, and then we'll go through them here in a moment. Okay, so now that you've had a chance to try these on your own and you've started the video back up, let's go ahead and talk about them together. So, the shortest fence, a 216 square meter rectangular pea patch, is to be enclosed by a fence and divided into two equal parts by another fence parallel to the other sides. What dimensions for the outer rectangle will require the smallest total length of fence? How much fence will be needed? Okay, so we have a rectangle that looks like this, something like that. I have a length and a width, and I know that the area is 216 meters squared. So that means that we know 216 equals the length times the width. Okay, so now what we want to do is we want to divide the patch into two equal pieces with another fence that is parallel to one of the sides. So we're going to draw a line down the middle, and what that does is it breaks W up into W over 2 and W over 2, right? We break that W in half. So the total length of fence now that we need is what we're looking for. So we've got the total amount of fence is all the sides added together. So that would be 3 L's plus 4 W over 2's, which is 3L plus 2W. And now we can substitute in for either of these two variables using the area formula we have down here at the bottom. So if I solve, for example, for well, we could solve this for L. So L equals 216 over W, and we can substitute that in. So we've got F equals 3 times 216 over W plus 2W. And so 216 times 3 is 648. So this is F equals 648 W plus 2W. And so now to maximize that, what we can do is we can find the derivative of this. So F prime would be the derivative of 648 over W is the opposite of 648 over W squared plus 2. And then we can set this equal to 0 and solve for W. So multiply both sides by W squared, and we'd get 0 equals negative 648 plus 2W squared, right? Because the W squared would cancel when we multiply it times this term, and we'd get it by the 2. Add 648 to both sides, divide by 2, and then take the square root, which is 18. So W equals 18. And then we can find the length by plugging it into this formula. So L equals 216 divided by 18. Which is 12. And now, how much fence will be needed? We can plug that into our our original fence formula. So we've got our that the outside needs to be 18. To answer the first question, 18 meters by 12 meters is the dimensions, and then the amount of fence is 3 times 12 plus 2 times 18. So that's 72 meters of fencing. Okay. So that's the idea for that one. Okay. So now let's look at 24 here. So the trough in the figure is to be made to the dimensions shown. Only the angle theta can be varied. What value of theta will maximize the trough's volume? Well, once again, this is a prism, which is the same idea as the cylinder we looked at before and the rectangle we looked at before that. So the volume of this is going to be the area of the base times the height. Okay? And then the height we already know is 20, and the area of the base can be broken up into these three pieces. So we've got a volume equals well, let's look at these three pieces first, and then I'll come back over to this. So the height, the one thing we're missing in here is we don't know how long these two sides are either. Really any of the sides. But let's call these X, because these are the part of the ones we're going to care about. And then let's call these Y, because we don't know what these are. I know that that's a 1. So now we can start trying to write all of these in terms of theta. Okay, so we know the area of these two pieces are going to be the same. So let's just deal with the one on the left. And we can use some trig to try and find ways to relate theta to X and Y. So I know that sine of theta will equal Y over 1. And I know cosine of theta will equal X over 1. So I know theta is sine of Y, inverse sine of Y, and so theta also equals inverse cosine of X. Oh, actually, I don't think I want to take that step. But so leave those alone as they are. And then I know that the area of this triangle is going to be 1/2 base times height. And X and Y are the base and height. So this will be the area of this little triangular piece would be 1/2 X times Y, which means it's going to be area equals 1/2 cosine theta sine theta. And I know there are two of those, and then I know the area in the middle is going to be X times 1. And I know there are two of these areas, and there's one of these. So when I plug them in over here, I'm going to get cosine theta sine theta plus X, which is, sorry, we don't want to put an X there. So let's simplify this a little bit further over here before I go back to the volume. For X, I know to be cosine theta. So this area of the other piece is going to be cosine theta. So this will be cosine theta, sine theta plus cosine theta, all times the height, which is 20. Okay. And so then at this point, if you wanted to, you could just graph this. So we could try doing that. So if we graph this function using X instead of Y instead of V and X instead of theta, this would be cosine X times sine X minus plus cosine X. And then I forgot to multiply it all by 20. And then what we want to remember is that our value has to be, the biggest our value could be is 90 degrees, right? So if I go back to my picture real quick, if this thetas were 90 degrees, then it would just be a flat thing on the ground and it wouldn't hold any water. So we can change, if we want, the domain in here. So let's set the domain. Okay, so let's set the domain to go from 0 to 90 degrees, which is pi divided by 2. And then that gives us just this part of the graph. So then we can click and we can see that this happens at pi over 6, comma 25.98. Okay, so we get an answer of pi over 6, comma 25.98. And so that's one way to do it. The other way to do this is we could actually work it out. So let's see if we can pull that off. So this will be the volume, the derivative of this would be, right, the 20 comes along because it's a constant multiple. We have to use the product rule inside. So this is cosine theta times the derivative of sine theta plus the derivative of cosine theta times sine theta, and then plus the derivative of cosine theta for that other piece. So v prime equals 20 times the cosine theta times cosine theta, right? The derivative of sine theta is cosine theta, plus the derivative of cosine theta is negative sine theta times sine theta minus sine theta. And then we can do some multiplying. This is v prime equals 20 times cosine squared theta minus sine squared theta minus sine theta. And then I think what we need to do is use a trig identity and solve this using the fact that it's going to be like a quadratic. So this would be v prime equals 20 times 1 minus sine squared theta minus sine. So I can replace cosine squared theta with 1 minus sine squared theta minus sine theta. So set it equal to 0. Combine like terms over here, we get negative 2 sine squared theta minus sine theta plus 1. We can divide by a negative 20 on both sides, and we'll get 0 equals 2 sine squared theta plus sine theta minus 1. And then I think... well, what you can do now is you can use the quadratic formula, so you can set thine. So this looks like a quadratic, right? I've got something squared plus that same thing not squared plus a constant. So sine theta equals 1, the opposite of 1, so negative 1 plus or minus the square root of 1 squared minus 4 times 2 times negative 1 all over 2 times 2. So that's negative 1 plus or minus the square root of 9 over 4. So that's negative 1 plus or minus 3 over 4. And so we get sine theta equals either negative 1 or sine theta equals 1/2. And then that means theta either equals negative pi over 2, which is not in our domain, or theta equals pi over 6, which is exactly what we got when we plugged it into the calculator, when we graphed it. And so this is our answer. So what value of theta gives the maximum volume of the trough? Pi over 6. And that volume would be about 30 units, cubic units of feet. 30 cubic feet. Okay, so that's the idea there. And like I said, you didn't need to do all this work beyond what I have boxed there, but that's how you would do it using calculus. Okay, so those were all problems that involved maximizing areas or volumes or things like that, geometric things. So now let's look at ones that involve triangles more specifically. So let's look at some more that involve things like that. So the first one here says, Jane is 2 miles offshore in a boat and wishes to reach a coastal village 6 miles down a straight shoreline from point nearest the boat. She can row 2 miles per hour and can walk 5 miles per hour. Where should she land her boat to reach the village in the least amount of time? Okay, so what we've got is we've got the shore, and then we've got a boat out here, right? Okay, and this distance is 2 miles, and this total distance from here to here is 6 miles from the boat to the village. And the question is, what is the fastest way for Jane to row and then walk the rest of the way? So where should she put her boat so that we can reach the village in the shortest amount of time? Okay, so there are a few different things going on here. So what we're looking for is, this is a distance equals rate times time problem. Okay, so we've got distance equals rate times time distance equals rate times time. But the variable here we really care about is time. So that if we solve this for t equals distance over rate. So there's two different parts going on here. Her total time, which I'm going to call capital T, will equal the time in the boat plus her time walking. And for each of those, we're going to have a distance and a rate. Right? So her time in the boat is going to be her distance in the boat divided by the speed at which she can row, which is 2 miles per hour. And her distance walking, her time walking will be her distance walking over the rate at which she walks. So that's dB over 2 plus dW over 2. So then we don't necessarily know what any of those distances are, but we can start to plug in a variable and simplify. So for example, if I let this distance be x, so the distance that she doesn't walk, for example, is 1. I could also put it over here and have it be the distance she does walk, but that's going to make my life a little easier, I think. Then the distance she walks, right, will be 6 minus whatever that part she didn't walk is. And the distance she rode is going to be the square, I could use the Pythagorean theorem, and it's going to be the square root of x squared plus 4, x squared plus 2 squared. Okay, and so now we can substitute those into our formula. So time is going to be the square root of x squared plus 4 over 2 plus 6 minus x over 5. Okay, and so now what we're trying to do is minimize the amount of time it takes for her to make it there. So now you have two options now that you've written the equation, right? Once again, you can either use derivatives or you can graph this. So I'm going to go ahead and let's try it with derivatives real quick and see what we get. So the derivative of this first piece Let's go ahead and just graph it. I changed my mind. Okay, so let's graph it. So this is y equals the square root of x squared plus 4 divided by 2 plus 6 minus x divided by 5. And what we want to look for is we want to look for the minimum. Okay? And so the minimum happens, hopefully, if I can click on it, which for some reason it's not letting me. Okay. So y equals, let's try this one more time, equals the square root of x squared plus 4 divided by 2 plus 6 minus x divided by 5. And if we click on that point, it'll tell us that that's 0.878 0.873, comma 2.117. Okay, so where should she land her boat to reach the village in the least amount of time? 0.873 miles from her starting point. Okay, and that's all there is to that. You could also find that, like I said, by taking the derivatives and then simplifying. Okay, so let's try another one together. So the shortest beam. The 8-foot wall shown here stands 27 feet from the building. Find the length of the shortest straight beam that will reach the side of the building from the ground outside the wall. Okay. So, there's a few things going on here. One is the idea of similar triangles is going to be an important thing here. And so let's go ahead and look at these sides. So, first of all, we've got the height at which this hits the building. We've got this area that's left over between the beam and the wall. So let's call that one X because I don't know what else to call it. And then we'll call the length of the beam B. Okay. So one thing we can see right off the bat is the length of the beam squared is going to be equal to X plus 27 squared plus H squared. Okay, that just using the Pythagorean theorem, right? That's a pretty good place to start out. Now, where similar triangles come in is we have to remember that the ratio of corresponding sides of a similar triangle are equal to each other. So, for example, in the smaller triangle here, I know that this is x over 8, okay, are equal to each other. Actually, let's do it the other way around. I know that 8 over x is a ratio involving these two. And if I do the corresponding sides from the large triangle, h corresponds to 8 and x plus 27 corresponds to h. And so now this is a way we can replace h with x in this equation and figure out what b is. So if I multiply both sides by x plus 27, I get 8 times x plus 27 over x equals h, and now I can substitute in that equation. So b squared equals x plus 27 squared plus h plus 8 times x plus 27 over x squared. And now we could simplify this a little. So we get b equals the square root of x plus 27 squared plus 8x plus 216 over x squared. Okay, and once again, now that we've written the equation, we could find the derivative of that and set equal to 0 and solve, or we could just try to graph it. So y equals the square root of x plus 27 squared plus the square root of, plus 8x plus 216 divided by x squared. Okay, and we zoom out, and we're only looking at positive answers, and so we want to find the minimum value, the shortest the beam can be, and so that gives me the answer there. So the answer is 12, 46.87. So 12, 48.67, which I may have written wrong. No, 46.87, sorry. So that means x is 12, so this little piece needs to be 12 feet, and then the total length of the beam, the shortest the beam can be, is the shortest beam is 46.87 feet long. Okay, so there's another example. So why don't you guys flip over to the next page, pause your video, or actually, I did those a little wrong. I meant to have you all try that one, but let's just go ahead and go through two more examples together. If you want to pause your video and try these, you can, but we haven't really talked about ones like this yet, and then we'll go from there. So the 800-room mega motel chain is filled to capacity when the room charge is $50 per night. For each $10 increase in room charge, 40 fewer rooms are filled each night. What charge per room will result in the maximum revenue per night? Okay, so when it costs $50, they fill all 800 rooms. So cost rooms. If they charge $10 more, then the number of rooms goes down by 40. So that would be 760. So for every $10 it goes up, the number of people in the hotel goes down by $40. Okay, so what we want to do is we want to write an equation for revenue. Okay? Okay, so revenue is going to be cost times the number of rooms that are full. Cost per room times the number of rooms that are full. So if we let C be cost, the question is how many rooms are full? Well, so if C were 50, we need the number of rooms to be full to be 800. If the cost is 60, then we need the number of rooms that are full to be 740. Well, so I think the easiest way to try and do this is it would be start at 800 and then subtract from that 40 rooms for every 10 rooms that that it exceeds 50. So then subtract from that 40 rooms for the cost minus 50. right? So what this is 800 is our max. If we exceed 500 rooms, if we exceed 50, for every $10 we exceed, and then the one thing I'm missing here, I think, is I need to divide this by 10. So let's check and see if this works out. So the idea here is that when I plug in 60, I should subtract $40. And I'm obviously going to be able to simplify this a little bit. But the idea is, so if I plug in 60, this would be 60 minus 50 is 10. 10 divided by 10 is 1. 1 times 40 is 40. 800 minus 40 is 760. Okay, so that worked. So then if I plug in 70, 70 minus 50 is 10. 10 divided by 20. 20 divided by 10 is 2. Yeah, so that's going to work. Okay, so let's simplify this a little bit, because right now it's a very complicated way to write this. So that would be 80 minus 800 minus 40 times c is 40c, divided by 10 is 4c, so minus 4c, and then 40 divided by 10 is 4 times 50 is 200. So this would be plus 200. So in the end, we end up with R equals C times 1,000 minus 4C, or R equals 1,000 C minus 4C squared. And now this is one we should be able to do by hand. That's a thing we can find the derivative pretty easily. So we take the derivative of that, and we get 1,000 minus 8C, set it equal to 0, and solve. We get 8c equals 1,000. C equals 1,000 divided by 8, which is 225. So they will maximize their profit if the cost per room is $225 per night. And if you want to check on that, you can graph it. So graph. Or you could even, well, yeah, so if you want to check on that, you could graph it. So let's try one more of these. So you operate a tour service that offers the following rates: $200 per person. If you want to pause here, sorry, you can. It's going to be similar to the problem we just did, but let's go ahead and go through it. So $200 per person if 50 people, the minimum number to book the tour, go on the tour. For each additional person, up to a maximum of 80 people total, the rate is reduced by $2. If it costs $6,000 plus $32 per person to conduct the tour, how many people does it take to maximize your profit? So there is one small difference here, which is profit equals revenue minus cost. So we're going to have two pieces to this equation. So the revenue piece is that I charge $200 per the number of people that go on the tour. So if 50 people go on the tour, I charge $200. For each additional person, the price goes down by $2. So we're going to use a similar formula to the one up here. So it's, not 200. We're going to use that, but not there. So it's going to be the cost per person. So it's going to be the number of people that go on the tour is going to be $200, but I'm going to subtract $2 for each person beyond 50 that goes on the tour. So I'm going to subtract $2 for each person that's over 50. Okay? And in this case, I don't need to divide by anything because I'm going up by ones. So that's where the 10 divided by 10 came from in the previous problem. Then from that, I'm going to subtract my cost. So my cost is $6,000 plus $32 per person. So that's 6,000 plus 32 times n. Okay, so then we simplify all this, and that will give us our profit function. So this will be 200 minus 2n minus 2 times 50 is 100 minus 6,000 minus 32n. So this is P equals n times 100 minus 2n minus 6,000 minus 32n, which I wrote in a really poorly in the previous step. Okay, and then distribute, so p equals 100n minus 2n squared minus 6,000 minus 32n. Combine like terms, and we get negative 2n squared plus 68n minus 6,000. And once again, we should be able to do this one by hand, but you could graph it instead. So find the derivative, which is negative 4n plus 68. Set it equal to 0 and solve. So we get 4n equals 68. And so n equals 17. So to maximize the profit, you want to have 67 people go on the tour. I feel like I did something wrong on this one. No, we got the right answer. 17 in addition to the ones we started with. So in addition to the 50 people. So this would be 67 people go on the tour. Okay, so that's it for our section 4.5 notes. Don't forget to be doing the homework assignments and checking my math lab for due dates. Due dates will go up on Mondays now, and everything will be due on Sundays at 11:15.